Today we're going to finish section 11.5 and we're going to talk about combining different events by using the word and. This, just like our OR problems that we just looked at, relates directly back to what we did in chapter 2 when we were looking at sets. So when we were looking at sets and we were thinking about the word intersection, we commonly use the word and to describe that. So as we're looking at our Venn diagram, that's what we are thinking about in these cases as well. Okay, our intersection represents the word and. When we are going through and talking about problems, in some cases we will have maybe a Venn diagram that we are looking at and determining a probability from that. In other cases, we're going to be given or be looking at some different probabilities, and in order to find our and, we're going to be combining those using our multiplication formula or multiplication rule and multiply those two probabilities together to get our probability of both happening. Before we get into some examples using our formula, we're going to look at just a basic Venn diagram here. So this Venn diagram shows information about 6 people. Suppose we select a person at random. What is the probability that the person is wearing a hat and glasses? So using our Venn diagram, thinking about intersection being our and, we're just looking for those 2 people in the middle. Okay. We have 6 people total in our Venn diagram. So our probability is 2 out of 6, which then reduces to 1 out of 3. Right, more often than not, when we're doing and probability questions, we are not going to be given a Venn diagram to start with. So what we want to be able to do is we want to be able to take 2 different probabilities and multiply them together. In this next example that we're looking at determining probabilities by drawing cards. Notice that as we're going through these examples, we do see the 2 different phrases, with replacement and without replacement. So that is definitely something that we want to keep in mind as we're going through and working on these problems. So for example 6a, 2 cards are to be selected with replacement from a deck of cards. So what this means is, as we're thinking about these, with replacement means that both time we are drawing a deck from a card from our entire deck of cards. And so our probability of 2 queens is going to be the probability that our first queen is selected times our probability that our second queen is going to be selected. All right, the probability for our first queen. Thinking about our deck of cards, well, we have 4 queens out of a deck of 52 people. Now, if we replace this, our next probability that we're looking at is still going to be the same. So we're still going to have 4 out of 52 people. We can reduce both of these to 1 out of 13 times 1 out of 13. If we multiply across in our fractions, we get 1 out of 13 squared is 169, which if we turn that into a decimal, we get 0.0059. So when we're doing with replacement problems, our denominators are remaining the same. For example B, we're asked the same question, but we're asked without replacement. So our basic setup is going to be the same. We're going to start by looking for our probability of 2 queens, and we're going to take the probability of our first queen times the probability of our second queen. The probability of our first queen is still 4 out of 52. Now the difference is here we are not replacing that card. So that means if we think about what we have left, well, if we've taken 1 queen out, we have exactly 3 queens left in our deck of cards. So our numerator is now going to be 3 instead of 4. If we've taken a card out of our deck of cards, we no longer have 52 cards, we have 51 cards. So when we're dealing with problems and we're thinking about doing these without replacement, right, we are changing both our numerator and our denominator. Right, if we reduce both of these fractions, this turns into 1 out of 13 times 1 out of 17, because 51 is evenly divisible by 3. That's going to give us 1 out of 221 or if we're asked to change it to a decimal, 0.0045. So as we're working through these problems, the key thing that we want to be looking at are these words with replacement or without replacement if we're looking at a deck of cards or something along those lines. Right, so this idea of with replacement and without replacement directly ties into the next vocabulary word that we have here. So event A and event B are independent events if the occurrence of either event in no way affects the probability of the other event. Rolling dice, flipping coin, and drawing cards with replacement are independent events. If we go back up and look at our previous example, right, our probabilities didn't change. So with replacement are examples of independent events. Dependent events occur when our first event does affect the second event. So example B up here where we had our two different probabilities, that is a good example of a dependent set of dependent events because our probabilities changed. Right, so down at the bottom here, we are asked a couple of questions about whether or not we have independent or dependent events. 100 people attended a charity benefit. 3 people in attendance will be selected at random without replacement, and each will be awarded one door prize. Are the events of selecting 3 people who will be awarded a door prize dependent or independent? So what we want to look at here is we want to look at our phrase without replacement. Without replacement, just like it did in example 6, is going to change our denominators for our probabilities. Right? Anytime we're dealing with something where our probabilities changed, right, depending on the event that happened before it, we call those dependent events. Right, then for example B, a coin is flipped 3 times, and it is recorded each time if the coin lands with heads or tails up. Is flipping the coin 3 times dependent or independent? Right, we're told above, and if we think about this, each flip that we have does not affect another toss. So in this case, tossing a coin is a good example of independent events. Right? So tossing a coin, rolling a die, or drawing cards with replacement are independent events. Right? Our first toss does not affect the other tosses. All right, so the last example that we're going to look at, and we're going to use our multiplication rule. Right? So a new medicine was given to a sample of 25 of Dr. Clear's patients with flu symptoms. Of the total, 19 reacted favorably, 2 reacted unfavorably, and 4 were unaffected. 3 of these patients are selected at random. Determine the probability of each of the following. So the first thing that we're going to look at is the probability that all of them reacted favorably. So that means we're going to take a probability of our first person reacting favorably times our probability, so we'll call that 1 favorably, that person 2 reacts favorably, and person 3 reacts favorably. All right, looking at these probabilities then. In our total, it's told that 19 reacted favorably. So we're going to start by taking 19 out of 25. Right, now the way that this one is set up, we're going to assume that we are not going to replace these people. We want to select 3 different people, not 3 of the same people over and over and over again. Right, so that means when we multiply it by our next probability, right, our probability that the second person reacts favorably, well, we've removed 1 from our group. So instead of 19, now we have 18. Instead of a total of 25, we now have a total of 24. Our last person then, well, now we have 17 people left to choose from that have reacted favorably out of 23 total. We're going to reduce our fractions as much as we can. All we can do here is cancel out a little bit with our 18 and 24. We're going to divide those both by 6 to get a 3 and a 4. And then we're going to multiply what we have straight across. So 19 times 3 times 17 is going to give us 969. Out of 25 times 4 times 23 is going to give us 2300, which we could then write as a decimal as 0.421, or about 42%. So about a 42% chance that all three are going to react favorably. In example B, we are asked that the probability that the first person reacts favorably, the second person reacts unfavorably, and the third person is unaffected. So we're going to take all three of these probabilities and we're going to multiply them together. All right, so the probability that our first person reacts favorably, just like it was in the previous example, is going to be 19 out of 25. Probability that the second person reacted unfavorably. If we go back up to our paragraph at the top, we are told that 2 people react unfavorably. So our numerator is going to be 2. Our denominator is going to be 24. And just like we did in example A, we're not replacing these people, so our denominator is going to decrease by 1 every time. Probability that the third patient was unaffected. Right, we had 4 that were unaffected, so we're going to multiply this to 4 over 23. Right, we're going to reduce 2 and 24. We can reduce to 1 and 12 by dividing them both by 2. Our 4 and our 12 we can reduce dividing those both by 4, leaving us with 1 and 3. And then if we multiply what we have left, 19 times 1 times 1 is 19. 25 times 3 times 23 gives us 1,725, or as a decimal, 0.011. So about a 1% chance that the first person reacted favorably, the second unfavorably, and the third person was unaffected. Okay. All right, in example C, right, we are asked to find the probability that none reacted favorably. Right? No patient reacted favorably. So we're going to say the probability that none reacted favorably. Okay. So not favorably is actually going to include both of our other possibilities. So as we're thinking about these people that reacted not favorably, it's not that they're unfavorable. Right? They could be unfavorable or unaffected. Right? So we have 19 people total that reacted favorably, 2 reacted unfavorably, and 4 were unaffected. That means that 6 either reacted unfavorably or were unaffected. So our first probability for here is going to be 6 out of 25. Our next probability, well, out of those 6, we've already chosen one, so we have 5 left. Out of that 25, we've chosen one, so we're selecting out of 24. And then for our last one, we're going to take 4, because we've already selected 2 people out of 23. I'm going to go ahead and do some canceling here. 5 and 25, we can divide both by 5. We get 5 and 1. We can cancel between our 6 and 24. Divide them both by 4, we get 1 and 4. And then our 4s are actually exactly the same, so we can divide those out to get a couple of 1s. So what we have left, 1 times 1 times 1 is 1. 5 times 1 times 23 is 115. So 1 out of 115, or 0.009. Right. As I'm working through these, I'm showing these using fractions for all of our different steps. You can choose to use fractions. You can multiply them and then change them to the decimal at the end. Just pay attention as you're entering the values on my math lab that you're answering them in the correct form. All right, so our last example then for number 7 is the probability that at least one patient reacted favorably. We're going to tie in our idea of our complement here. Right? So our probability that at least one person reacted favorably, right, is the complement of the event that none of them did. Right? We don't necessarily want to go through and find all of the different possibilities. So what we're going to do is we're going to say, well, the opposite of none means that at least one person did. Right? So as we're thinking complements, remember we subtract from 1. So we're going to take 1 minus our 1 out of 115, which is going to give us 114 out of 115. Or if we subtract as a decimal, 1 minus 0.009 gives us 0.991. So we have about a 99% chance that at least one patient reacted favorably. Right? So as you're going through your homework, if you see a question that looks like this, none and at least one, remember, are complements. So once we have the answer to none, we can use that to nicely get us our answer to at least one pretty quickly without a lot of work.